Event sourcing. There are some parallels between the ideas we've discussed here and event sourcing, a technique that was developed in the domain-driven design DDD community. We will discuss event sourcing briefly, because it incorporates some useful and relevant ideas for streaming systems. Similarly to change data capture, event sourcing involves storing all changes to the application state as a log of change events. The biggest difference is that event sourcing applies the idea at a different level of abstraction. In change data capture, the application uses the database in a mutable way, updating and deleting records at will. The log of changes is extracted from the database at a low level, for example by parsing the replication log, which ensures that the order of writes extracted from the database matches the order in which they were actually written, avoiding the race condition in Figure 11-4. The application writing to the database does not need to be aware that CDC is occurring. In event sourcing, the application logic is explicitly built on the basis of immutable events that are written to an event log. In this case, the event stores appendingly, and updates or deletes are discouraged or prohibited. Events are designed to reflect things that happened at the application level, rather than low-level state changes. Event sourcing is a powerful technique for data modeling. From an application point of view, it is more meaningful to record the user's actions as immutable events, rather than recording the effect of those actions on a mutable database. Event sourcing makes it easier to evolve applications over time, helps with debugging by making it easier to understand after the fact why something happened, and guards against application bugs. See advantages of immutable events on page 460. For example, storing the event student canceled their course enrollment clearly expresses the intent of a single action in a neutral fashion, whereas the side effects one entry was deleted from the enrollments table, and one cancellation reason was added to the student feedback table embed a lot of assumptions about the way the data is later going to be used. If a new application feature is introduced, for example, the place is offered to the next person on the waiting list, the event sourcing approach allows that new side effect to easily be chained off the existing event. Event sourcing is similar to the Chronicle data model, and there are also similarities between an event log and the fact table that you find in a star schema. See stars and snowflakes. Schemas for analytics on page 93. Specialized databases such as Event Store have been developed to support applications using event sourcing, but in general the approach is independent of any particular tool. A conventional database or a log-based message broker can also be used to build applications in this style. Deriving current state from the event log, an event log by itself is not very useful, because users generally expect to see the current state of a system, not the history of modifications. For example, on a shopping website, users expect to be able to see the current contents of their cart, not an append-only list of all the changes they have ever made to their cart. Thus, applications that use event sourcing need to take the log of events representing the data written to the system and transform it into application state that is suitable for showing to a user the way in which data is read from the system. This transformation can use arbitrary logic, but it should be deterministic so that you can run it again and derive the same application state from the event log. Like with change data capture, replaying the event log allows you to reconstruct the current state of the system. However, log compaction needs to be handled differently. A CDC event for the update of a record typically contains the entire new version of the record, so the current value for primary key is entirely determined by the most recent event for that primary key, and log compaction can discard previous events for the same key. On the other hand, with event sourcing, events are modeled at a higher level. An event typically expresses the intent of a user action, not the mechanics of the state update that occurred as a result of the action. In this case, later events typically do not override prior events, and so you need the full history of events to reconstruct the final state. Log compaction is not possible in the same way. Applications that use event sourcing typically have some mechanism for storing snapshots of the current state that is derived from the log of events, so they don't need to repeatedly reprocess the full log. However, this is only a performance optimization to speed up reads and recovery from crashes. The intention is that the system is able to store all raw events forever and reprocess the full event log whenever required. We discuss this assumption and limitations of immutability on page 463. The event sourcing philosophy is careful to distinguish between events and commands. When a request from a user first arrives, it is initially a command. At this point it may still fail, for example because some integrity condition is violated. The application must first validate that it can execute the command. If the validation is successful and the command is accepted, it becomes an event, which is durable and immutable. For example, If a user tries to register a particular username or reserve a seat on an airplane or in a theater, then the application needs to check that the username or seat is not already taken. We previously discussed this example in fault-tolerant consensus on page 364. When that check has succeeded, the application can generate an event to indicate that a particular username was registered by a particular user ID, or that a particular seat has been reserved for a particular customer. At the point when the event is generated, it becomes a fact. Even if the customer later decides to change or cancel the reservation, the fact remains true that they formerly held a reservation for a particular seat, and the change or cancellation is a separate event that is added later. A consumer of the event stream is not allowed to reject an event. By the time the consumer sees the event, it is already an immutable part of the log, and it may have already been seen by other consumers. Thus, any validation of a command needs to happen synchronously before it becomes an event, for example, by using a serializable transaction that atomically validates the command and publishes the event. Alternatively, the user request to reserve a seat could be split into two events, first a tentative reservation, and then a separate confirmation event once the reservation has been validated, as discussed in implementing linearizable storage using total order broadcast on page 350. This split allows the validation to take place in a synchronous process. State, streams, and immutability. We saw in Chapter 10 that batch processing benefits from the immutability of its input files, so you can run experimental processing jobs on existing input files without fear of damaging them. This principle of immutability is also what makes event sourcing and change data capture so powerful. We normally think of databases as storing the current state of the application. This representation is optimized for reads, and it is usually the most convenient for serving queries. The nature of state is that it changes, so databases support updating and deleting data as well as inserting it. How does this fit with immutability? Whenever you have state that changes, that state is the result of the events that mutated it over time. For example, your list of currently available seats is the result of the reservations you have processed. The current account balance is the result of the credits and debits on the account, and the response time graph for your web server is an aggregation of the individual response times of all web requests that have occurred. No matter how the state changes, there was always a sequence of events that caused those changes. Even as things are done and undone, the fact remains true that those events occurred. The key idea is that mutable state and an append-only log of immutable events do not contradict each other. They are two sides of the same coin. The log of all changes, the changelog, represents the evolution of state over time. If you are mathematically inclined, you might say that the application state is what you get when you integrate an event stream over time, and a change stream is what you get when you differentiate the state by time. As shown in Figure 11-6, the analogy has limitations. For example, the second derivative of state does not seem to be meaningful, but it's a useful starting point for thinking about data. Figure 11-6, the relationship between the current application state and an event stream. If you store the changelog durably, that simply has the effect of making the state reproducible. If you consider the log of events to be your system of record, and any mutable state is being derived from it, it becomes easier to reason about the flow of data through a system. As Pat Halland puts it, transaction logs record all the changes made to the database. High-speed appends are the only way to change the log. From this perspective, the contents of the database hold a caching of the latest record values in the logs. The truth is the log. The database is a cache of a subset of the log. That cached subset happens to be the latest value of each record and index value from the log. Log compaction, as discussed in log compaction on page 456, is one way of bridging the distinction between log and database state. It retains only the latest version of each record and discards overwritten versions. Immutability in databases is an old idea. For example, accountants have been using immutability for centuries in financial bookkeeping. When a transaction occurs, it is recorded in an append-only ledger, which is essentially a log of events describing money, goods, or services that have changed hands. The accounts, such as profit and loss or the balance sheet, are derived from the transactions in the ledger by adding them up. If a mistake is made, accountants don't erase or change the incorrect transaction in the ledger. Instead, they add another transaction that compensates for the mistake, for example, refunding an incorrect charge. The incorrect transaction still remains in the ledger forever because it might be important for auditing reasons. If incorrect figures, derived from the incorrect ledger, have already been published, then the figures for the next accounting period include a correction. This process is entirely normal in accounting. Although such auditability is particularly important in financial systems, it is also beneficial for many other systems that are not subject to such strict regulation. As discussed in Philosophy of Batch Process Outputs on page 413, if you accidentally deploy buggy code that writes bad data to a database, recovery is much harder if the code is able to destructively overwrite data. With an append-only log of immutable events, it is much easier to diagnose what happened and recover from the problem. Immutable events also capture more information than just the current state. For example, on a shopping website, a customer may add an item to their cart and then remove it again. Although the second event cancels out the first event from the point of view of order fulfillment, it may be useful to know for analytics purposes that the customer was considering a particular item, but then decided against it. Perhaps they will choose to buy it in the future, or perhaps they found a substitute. This information is recorded in an event log, but would be lost in a database that deletes items when they are removed from the cart. Deriving several views from the same event log, moreover, by separating mutable state from the immutable event log, you can derive several different read-oriented representations from the same log of events. This works just like having multiple consumers of a stream figure 11-5. For example, the analytic database Druid ingests directly from Kafka using this approach. Pistachio is a distributed key-value store that uses Kafka as a commit log, and Kafka Connect Syncs can export data from Kafka to various different databases and indexes. It would make sense for many other storage and indexing systems, such as search servers, to similarly take their input from a distributed log-C keeping systems in sync on page 452. Having an explicit translation step from an event log to a database makes it easier to evolve your application over time. If you want to introduce a new feature that presents your existing data in some new way, you can use the event log to build a separate read-optimized view for the new feature and run it alongside the existing systems without having to modify them. Running old and new systems side by side is often easier than performing a complicated schema migration in an existing system. Once the old system is no longer needed, you can simply shut it down and reclaim its resources. Storing data is normally quite straightforward if you don't have to worry about how it is going to be queried and accessed. Many of the complexities of schema design, indexing, and storage engines are the result of wanting to support certain query and access patterns. See Chapter 3. For this reason, you gain a lot of flexibility by separating the form in which data is written from the form it is read, and by allowing several different read views. This idea is sometimes known as command query responsibility segregation, CQRS. The traditional approach to database and schema design is based on the fallacy that data must be written in the same form as it will be queried. Debates about normalization and denormalization, see many-to-one and many-to-many relationships on page 33, become largely irrelevant if you can translate data from a write-optimized event log to read-optimized application state. It is entirely reasonable to denormalize data in the read-optimized views, as the translation process gives you a mechanism for keeping it consistent with the event log. In describing load on page 11, we discussed Twitter's home timelines. A cache of recently written tweets by the people a particular user is following, like a mailbox. This is another example of read-optimized state. Home timelines are highly denormalized since your tweets are duplicated in all of the timelines of the people following you. However, the fanout service keeps this duplicated state in sync with new tweets and new following relationships, which keeps the duplication manageable. The biggest downside of event sourcing and change data capture is that the consumers of the event log are usually asynchronous, so there is a possibility that a user may make a write to the log, then read from a log-derived view and find that their write has not yet been reflected in the read view. We discussed this problem and potential solutions previously in Reading Your Own Writes on page 162. One solution would be to perform the updates of the read view synchronously with appending the event to the log. This requires a transaction to combine the writes into an atomic unit. So either you need to keep the event log and the read view in the same storage system, or you need a distributed transaction across the different systems. Alternatively, you could use the approach discussed in implementing linearizable storage using total order broadcast on page 350. On the other hand, deriving the current state from an event log also simplifies some aspects of concurrency control. Much of the need for multi-object transactions, see single-object and multi-object operations on page 228, stems from a single user action, requiring data to be changed in several different places. With event sourcing, you can design an event such that it is a self-contained description of a user action. The user action then requires only a single write in one place, namely appending the events to the log, which is easy to make atomic. If the event log and the application state are partitioned in the same way, for example, processing an event for a customer in partition 3 only requires updating partition 3 of the application state, then a straightforward single-threaded log consumer needs no concurrency control for writes. By construction, it only processes a single event at a time. See also actual serial execution on page 252. The log removes the non-determinism of concurrency by defining a serial order of events in a partition. If an event touches multiple state partitions, a bit more work is required, which we will discuss in Chapter 12. Many systems that don't use an event-sourced model nevertheless rely on immutability. Various databases internally use immutable data structures or multi-version data to support point-in-time snapshots. See indexes and snapshot isolation on page 241. Version control systems such as Git, Mercurial, and Fossil also rely on immutable data to preserve version history of files. To what extent is it feasible to keep an immutable history of all changes forever? The answer depends on the amount of churn in the dataset. Some workloads mostly add data and rarely update or delete. They are easy to make immutable. Other workloads have a high rate of updates and deletes on a comparatively small dataset. In these cases, the immutable history may grow prohibitively large, fragmentation may become an issue, and the performance of compaction and garbage collection becomes crucial for operational robustness. Besides the performance reasons, there may also be circumstances in which you need data to be deleted for administrative reasons, in spite of all immutability. For example, privacy regulations may require deleting a user's personal information after they close their account. Data protection legislation may require erroneous information to be removed, or an accidental leak of sensitive information may need to be contained. In these circumstances, it's not sufficient to just append another event to the log to indicate that the prior data should be considered deleted. You actually want to rewrite history and pretend that the data was never written in the first place. For example, Datomic calls this feature excision, and the Fossil version control system has a similar concept called shunning. Truly deleting data is surprisingly hard, since copies can live in many places. For example, storage engines, file systems, and SSDs often write to a new location rather than overwriting in place, and backups are often deliberately immutable to prevent accidental deletion or corruption. Deletion is more a matter of making it harder to retrieve the data than actually making it impossible to retrieve the data. Nevertheless, you sometimes have to try, as we shall see in legislation and self-regulation on page 542.